Hi, in this video I'm going to show how to use the MATLAB Deep Learning Toolbox to automatically detect tumors in volumetric brain images taken from an MRI. The neural network that is going to be used is called a U-shaped neural network, which consists of several convolutional layers, max pooling and other layers. And it's called U-shaped because the input is going to be a 3D volume and the output is going to be a 3D volume. So you have to have an encoding phase in which the size of the volume decreases and the number of features increase, and eventually the size of the image has to increase back to have the segmented label image. So it's gonna go down encoding and then up back decoding, and that's why it's called a U-shape. And also for the input, for training the neural network, we're going to provide labels for the corresponding image. And the labels are volumes of the same size as the image, but instead of having colors, it's going to have the label indicating whether the element has a tumor or not. After using the training data, we're going to test the neural network with test data, test images, and labels, which are totally independent from the training data, to verify that the network was trained, is able to generalize well and able to predict whether the brain has a tumor or not, for data that it has never seen before. Okay, so let's start this example this is example I'm using, and the reference to this page is in the links below of this video. So let's open the live script. Okay. Okay, now let's run this. Let's put a breakpoint here. And in order to train a neural network, you need three things. Well, one of them is the data, and you have to do sometimes a significant pre-processing of this data in order to be able to feed it into the neural network, like we're going to do in this case. The second thing that you need is the model, the deep learning neural network, the layers and the connections between them. We're going to do that as well in here. And finally, you need the training options, that is which optimization algorithm we're going to use ADAM, which is adaptive momentum, and you also have to specify other deep learning hyperparameters in there. Once you have those three, you feed it into a function that is going to train the neural network and provide you a trained neural network that you can use to predict whether 3D volume has a tumor or not. Okay, so let's do that. And first, let's go and get the data for training and for testing and validation also. Okay, so the data is going to come from this website. It's going to be here. You go to the corresponding Google Drive and select this one and download it. And I'm not going to do it now because it takes a lot of time. So in the end, you're going to have something like this. You're going to have a folder for the images for training, a corresponding folder for the labels of training, which correspond to this one. And also there's a testing folder, but we're going to use it because it doesn't have labels. Later, we're going to download another independent test data in which you have images, five 3D volumes, and the corresponding 5 labels. And this is the one that we're going to use to validate our neural network. Okay, so let's go back to the folder, because we need these auxiliary functions to do this example, and if you are not in the path, it's going to break. Okay, so the example is going to try to use TempDir, which is in the C drive. Since I have in the C drive solid state drive is limited in the memory, I want this data in my magnetic drive, which is more abundant. Also, this data I think is a few gigabytes, so if your solid state drive is limited, then you might have to do something like this as well to point to the right folder. Okay, it's not going to create it because it's already created, and now we're going to have to do some pre-processing. We're going to do some normalization on the data. We're going to do some cropping, And also we're gonna copy the images from the GC extension to a mat file extension, and also we're gonna divide as you just saw. We don't have validation data, so we have to split the data into 3 chunks: one for training, another for validation, and another one for testing. We are going to use most of the data for training, 83% of the data. We're going to use 6% for validation, and the rest 8 and 11% for testing. Okay, so let's do that pre-processing. We're gonna put here. Here's the source, where the files that we just downloaded, and here's where we're gonna place the pre-processed 3D images. But again, he's pointing to temp dir, which is in my C drive, so I have to put the right folder location, which is in the D drive. Okay, let's go inside there to see what happens in the pre-processing. This is one of the auxiliary methods that comes with example. Okay, so this is the folder where the training image comes from and the label images come from. This is the source. Okay, so we're gonna do some moving of hidden files. I'm not gonna go through the details of this. It's already done. Basically, there's some garbage that comes with this downloaded data. Okay, so it's gonna go here if the preprocessed file do not exist, or if it is not complete, which is what this function is doing. Okay, so the first is gonna create the 3 folders: one for training, images and labels, validation, and testing. And these images come from an MRI, so we're gonna use this method that is from the image processing toolbox to load the MRI data. We're gonna use a data store for that. We specify where the volumes, the images are coming from, where the labels are coming from. For the case, for the labels, we're going to use a pixel label data store that you have to provide the class names, which is the class names are background on tumor, and the pixel labels are 0 and 1. And the file extension is this one, the same is with this one, and we're going to use the volume reader. And notice this one. For label reader, we are going to read the value, and if it is higher than 1, then it's going to be a boolean. The result is going to be a boolean what we read from the labels. So okay, so we're going to use this and this format reader as the callback for the data store. It's going to be our callback. Okay, so we're going to read one data at a time from there. So okay, so we're going to reset the data stores. Then this is a method from the data store. You can call the method as a function, passing the data store as an argument, but in reality, this can be called like this as well. And when you read data like this from a data store, or this one, this can be read like these are methods of the data store like this. Okay, once you read the labels and the data, we're going to use this image processing toolbox function, which is very useful. It basically provides you information like the centroid, the volume. I think it provides a volume as well, or yes, volume, the area. This is for 3-dimensional. For 2-dimensional image, instead of having volume, you have area. Also, we have a bounding box. That's what the property that we are using here. There's a definition somewhere, but anyway, this bounding box is going to be used to capture the actual image, and then once you have that region, we're going to clamp it. We're going to put it as a region of interest, and basically we're going to filter some pixels out. And yeah, and this right here, once you have the cropped volume, then we're going to do the normalization in there. In here, the normalization is basically taking the mean of all dimensions, the standard deviation, and then subtracting the mean and dividing the standard deviation This is basically what a normalization layer does in deep learning. And actually, the neural network that we're going to use in the first layer, there is normalization. So we're going to see later how that is taken away because we are doing it right here. And also we are changing the values we're going to convert it to a range between 0 and 1 by first clamping it and then clamping it here and then doing this to set the values between 0 and 1. Okay, so that's for normalization. And finally, we're also cropping the labels, and 83% of the file is the file number. The ID of the file is below 83%, that is going to be placed in the training folder. The other 6%, 89 minus 83 is 6, so 6% is going to validation, and the rest 11% goes to testing. Once you have the folder, then the corresponding crop volume and crop label here is going to be saved into that math file, and that math file is the one that we're going to use for the data stores that we're going to feed to the neural network. Okay, so that's pre-processing. Yeah, I went through all of this. This is just a condition that you need to check. Okay, so let's get out of the pre-processing. No, this is not the right place. Okay, let's just just hit F5 to get out of here. Okay, nothing was done here because the proper processing was already done. And you can see the result is going to be this folder in which you have a set of image data for testing, the corresponding labels for testing, the image for training, the corresponding labels for training, and validation as well. So this is the result, and notice that they are map files. The original data was GC files. Okay, so we have the data ready. Now we're gonna create the data store so we can feed it to the neural network. Okay, for the image, the brain 3D image, we're gonna use an image data store, and we're gonna specify the extension, which is a mat file, and since it is a mat file, which is not a non-standard format, then we have to provide a callback. Let's take a look at that callback. Okay, whoops, we're in the wrong folder, you see. Wow, okay, it created it. That's not good. Anyway, in order to make the example run, we have to be in the folder where, and this is the callback function that we are using. It's very simple. It's basically going to load the file, and then get, the volume is going to be a variable, and it's going to be within a structure. So you have to find the field of structure and get the corresponding field, and that's how you extract the data. It's very simple. We're going to see it in a moment. So that's a callback, and notice that this volume reader is going to be used in a bunch of places to create various data stores. So yeah, you have to provide the reader. And okay, so we create the location is going to be the folder of the pre-processed data that we just created. That's going to be the location for the data store. And we're going to do exactly the same for the labels. We provide the location, which is in the same folder. We have to provide the categories, background and tumor, 0 and 1 in here, and also the same volume reader to read from the mat file. That's it. So as mentioned before, to train the neural network, you have to provide the brain images, 3D images, plus the corresponding expected segmentation value, which is the label images. That's why we use using the pixel label data store for. So with the expected value, the neural network training algorithm is going to subtract the output from the neural network from the expected value to get the gradient that is used to compute the modification of the weights of the neural network. So that's how the neural network is trained. Okay. Okay, and now we have a breakpoint here. Notice that the callback is not executed until we read data from the data stores. Okay, so let's call preview, and preview is gonna load it's gonna call the callback. Now you notice that we have a structure containing the variable inside, so we need to get the fields, and for the fields we only have one, so the only one that we use The only one that we have is the one that we use, and like that we get the crop variable like this. And notice that the brain image is a three-dimensional. It has 4 dimensions, and the last dimension is for the modalities of the MRI. So you have 4 modalities. Okay, and that's gonna be those 4 dimensions are gonna be input for the neural network. Okay, now let's read. Oops, let's put a breakpoint in here. Let's hit F5 to continue. And now we are in the label. And again, the label has a structure, crop label, the fields, which crop label, take the first one. And notice that the label, instead of being 4 dimensions, is 3-dimensional. It's a logical array because the values of the tensor is going to be 0 or 1, 0 indicating no tumor and 1 indicating tumor. Okay, so let's just hit F5. Okay, and now we're gonna put the brain image and the labels together so that we can visualize it. We're gonna use a UI panel using the figure command from MATLAB, and then the label volume show we're gonna use to put the labels, the label that we just read from the data store, against the volume. This is the training data again. And for the volume, in order to display the volume, we cannot display the 4 dimensions, so we have to pick the first modality to pick a brain volume. We provide the panel that we just created here, and this color map for the categories of the label, which is 0 for the background and red for the tumor. This is red, green, blue. Okay. Yeah. So this is black and red, but notice that the background is covering everything. So the tumor is just a small part, and the rest is background. It's non-tumor. So if we, by default, when you use label show, uh, both labels are going to be displayed, but we don't want to display the background because everything is hidden. So the background is 1 and the tumor is 2. So we're going to hide by setting this property of this label volume show to 0. And now we can see the tumor in here placed together with the brain image. And we can see like this, and like the volume viewer, you can zoom it and rotate it with the same, and you can see a tumor in there. Okay. Now let's okay, so one advantage of this image is that it's very big. So usually in a neural network, to train the neural network, you have to supply many images. But in order to, but it's sometimes it's not easy to get a large amount of images. So one of the strategy, especially when we have a big image, is to split it into different patches. I mean, for example, let's take this patch over here, this part of the volume, and feed it to a neural network, and the categories in here it doesn't contain a tumor. Then let's pick up this a sub volume which contains a tumor and feed it to a neural network. So for doing that partitioning of volume, we use the random patch extraction, which is a data store from the deep learning toolbox, and that is going to randomly pick up these different volumes. And by doing that, you are multiplying your data, because if we take let's say 100 patches, then you have 100 data samples per image. So if you have, let's say, 200 images, the amount of images that we have in here. Okay, no, those are the tests. So let's say in here we have like 30 images, and you take 100 patches out of that. Instead of having 300 data points, now you have 30,000 data points. So that's gonna give more power for the neural network training. Okay. So let's create the random patch extraction data store and the random patch extraction is gonna do the extraction for the image, the input image, and the expected labels in the output. It's gonna do it for both at the same time. So you provide both the labels and the image to the neural network. So you provide the volume, the image and the data store, and provide the pixels data store. And also indicate the patch size. This is gonna be the size of the patch and the patches per image. Then we select 16 and the mini batch size is gonna be 8. Okay, now that we have the random patch extraction data store, we're gonna do the same. We did data store for the training data, but we have also to do the same for the validation data. Okay, again, the difference between training, validation, and test data sets is the following. A training is the data that is going to be fed to the neural network that the output is used in the gradient computation to update the weights of the neural network. That is, the training data is the one that is used to update and train the neural network. The validation is going to be used independently from the training data to assess how well your neural network is generalizing. Because one of the challenges in deep learning training is that, okay, you can provide all the data in the world and the neural network can really adapt to that data, but once you provide data that the neural network is never seen before, it can be way off. So that means that your neural network did overfitting. It's not generalizing well. So for that, you reserve some of the data for validation. So the neural network, when training, for each batch, is gonna update the weights of the neural network, and at that point, it's gonna compare against the validation data and see how the precision is increasing over time. Because you can have, okay, if you are overfitting, you can get to a precision of 99% with the training data, but then you can have 70% of accuracy with the validation data, and then you are realizing, okay, I'm overfitting. I need to do better generalization, and then that's when you enter to regularization strategies. Regularization strategies can include using rectified linear unit layers, can include using dropout layers, can include other things, dealing doing some trick with the data. So there are various ways to regularize and to avoid that your model overfits in order to generalize well. So that's why you need to provide a validation data. Okay, so let's create the data stores for the validation data in the same way that we did it for the training data. Okay, so we provide the location, which is in the preprocessed data location. Again, we use the same callback for reading the math file. It works exactly the same. We do the same thing for the labels of validation, create the data store, and also we're gonna do some random patch extraction data store. We're gonna have this data store that takes the volume and the pixel. Data store, the same patch size and the same patch per image. Okay. Finally, we are gonna do some data augmentation. Data augmentation, what it's gonna do is gonna apply some affine transforms to the image. Affine transforms mean rotation, translation, shearing, flipping vertically, horizontally, some subset of that or a combination of them. And the reason why that is done is to even multiply even more your data. For example, let's say that this image, you flip it vertically, you flip it horizontally, then you have 3 additional copies, 3 different additional training points for your neural network. So if before, by doing random patch extraction, we multiply our data to 30,000 samples. Now, if we do data augmentation, we can make it look like it is 100,000 data samples. That is one of the purposes of augmentation, which is very useful for computer vision applications and also for 3D volume images to be able to train the neural network better. But it doesn't only augment the size, the amount of samples, but also it makes it more robust. Because, for example, I can train the neural network to detect the tumor from this perspective. But what about if I flip it? Then it's not going to detect it. But if we do this augmentation of flipping the orientation, rotating, then the neural network is going to be able to detect the tumor independently if it is pointing to the east or pointing to the west. So it's going to make the training more robust. Okay, so now we do this data augmentation by using a transform that takes as an input a data store, and it's going to output another data store. And for the data, it's going to read the data and it's going to apply a callback function. The callback function is going to be this one, and then this function is going to transform and give us the data for the output data store. And this is data store that we're going to feed to a neural network directly. Okay, so let's take a look at this function. Okay, let's put a breakpoint here. Again, when the data store is created, the callback function is not called. It's called when the data is read. Okay, notice that this function is going to be used both for training and validation. So this argument is going to tell, okay, I'm using this function for training, or I'm using this function for validation, because the function is going to behave differently for both. And this patch in is basically the data that is being read from here. Okay. Okay, so again, in the beginning I mentioned that to train a neural network, you need data, you need a model, the layers of the neural network, and you need the training options. We already provided the data, which is very laborious, as you see, and now we're gonna create the neural network. You can create it manually, but also you can use a pre-trained neural network and do additional training on top of it. In this case, we're going to use this function to create a neural network. Okay, so this is from the this is from the computer vision toolbox. Is what I mentioned before. It's called UNet because it has some encoding phase and decoding phase. It has a set of convolutional neural networks. We're gonna see how it is in a moment. Okay, so we specify the input, which is the patch size 132 to the cube and 4 modes of the MRI, and the output number of classes, because this is for semantic segmentation classification, is gonna be the categories of 0, no tumor, and tumor. So that's what we provide to neural network. And the convolution is a neighbor processing operation that basically operates a kernel, which is the weights of the neural network into the image. And when that is done, it can go out of bounds of the image, and you have two options. Or to avoid going beyond the valid values, one of the options is basically reduce the size of the image, or keep the size of the image as is by adding padding. So we're going to choose adding padding. Okay, so this is going to give us our layers. Okay, so notice that the output patch size is going to be 44 to the cube. Okay, that's how this neural network decided it. Okay, so let's take a look at the neural network. We're going to use the analyze network function that is going to bring us an application to analyze the layers. Okay, so in here we have the encoding phase. The input is going to be the patch 132 to the cube and 4 modes of the MRI. Notice that we have a zero-center normalization, and we don't need this, so we're going to take it away because we already did a normalization in the pre-processing of the data. Okay, so it's going to have a set of convolution, rectified linear unit, batch normalization. As mentioned before, batch normalization, according to the Ian Goodfellow book of deep learning, it refers to subtracting the mean and dividing by the standard deviation to the weights of the neural network in order to avoid problems during the training of the network. A rectified linear unit is basically a layer in which the output is linear. The linearity in training of a neural network is convenient. It's very convenient for computing the gradients. And below 0, less than 0, the value is 0. That is a strategy for regularization to help the neural network to generalize better. And the convolution is good. As mentioned before, it's a neighbor processing operation, which is good to capture patterns, local patterns, while the max pooling is gonna be able to capture patterns within patterns, between patterns. So it's basically taking the maximum in a zone, in a stride zone, and it's gonna be able to capture these global properties eventually. And every time that you execute a max pooling, it's gonna divide the size of the image by 2. And you notice that at the beginning starts with the patch size, eventually decreases until it gets down to 9 by 9, while the number of features increase until it gets to a point of 170 100 something. And then once you have all your features in here that you extract all the properties of the image, now you have to build it back so you can have the labeled image. So it's gonna use again convolution, batch normalization, but it's gonna use another variant of the convolution to be able to bring the size of the image up. Okay, so this is the decoding phase, and eventually it's gonna get to the size of 44 to the cube. And the output, instead of having a bunch of features, is gonna have the last dimension is gonna be 2. The number of features is gonna be 2, and that basically means the classification, the segmentation classification of having tumor or no tumor. Notice also that we have a segmentation layer, but we're gonna choose another layer for this. We're gonna show in a moment. Notice that the layers are connected in sequence, but we can also have some connections that go outside of the sequence, like this one. Okay. Okay, so now, okay, one of the problems with this data is that the tumors are, the number of tumors are small compared to the overall size of the brain. So the neural network is gonna be trained better for the background, the parts of the image that do not have tumors, because there's more data, so there's a bias towards that. So in order to compensate for that, we're gonna use the DICE pixel classification layer. DICE is because of the person that worked in this area. It doesn't mean that you're gonna roll dice or anything like that. Okay, so we're gonna create this layer, and we're gonna replace the last layer, which is called segmentation layer, with this layer. So we're gonna use the replace layer command. And we're gonna do something similar with the first layer, because we don't want normalization. So we're gonna create an identical image 3D input layer, and we're gonna have this patch size, which is the same size, but we're gonna set normalization to none. We don't want normalization, and the name is gonna be the same. So we're gonna replace the first layer, which is named the same way. And then finally, let's take a look to see if the network is as we expected to be. Okay, so we don't have normalization anymore. The sizes are the same. The network is basically the same, and we have the DICE pixel classification at the end with the same output size. Okay. Okay, now we have the data stores for the training the neural network. We have the neural network layers, and now we have to provide the options for training the neural network. For that, we use the training options command, and the first argument is the algorithm that is going to be used to train the neural network. As mentioned before, the algorithm is going to take the output of the neural network, and it's going to take the expected output, which is the labels images that we have been providing in the pixel label data store, and it's going to subtract them to compute the gradient. And from that gradient, using a loss formula, it's gonna accumulate some first order momentum and second order momentum to update the weights of the neural network for each batch. Okay, so that's how it basically is gonna update. At the beginning, the update is gonna be very high, and eventually the update is gonna be lower towards the end. So we start with this initial learning rate, and as the training progresses, it's gonna drop down by this factor, the learning rate, to make it slower. Each 5 batches, epochs. Each 5 epochs is gonna drop down the learning rate to make it slower as the training progresses. Because at the beginning you expect to have a bunch of errors, so that's why you want to learn faster at the beginning. But then towards the end, as it gets more stable and close to the solution, you want to learn slower. Okay, so we also provide the validation, because the training options are going to apply them to to assess how well it's generalizing, as mentioned before. Okay, so now notice that these training option functions is gonna call the data store, the validation data store is gonna read the data. So the breakpoint that we have in this data augmentation is gonna be hit. Okay, so we're gonna see it in a moment when we run this. Okay, we're running it now. The breakpoint should hit. Yeah, and notice that we're in the validation data, so the flag is going to be validation, but there's a bug in the documentation function. This function comes with the documentation and is comparing against lowercase validation. So when we run this, it's going to be 0 here. So this is supposed to be 1. Let's correct this. Yeah, now we have 1. And we pre-allocate memory for efficiency. This is going to be output, the output volume and the output response are going to be placed both of them in a table, and this is going to be the output for your function. Okay, now we're going to apply this augmentation. One of these 4. One of them is rotating 90 degrees, flip from left to right, which is flipping horizontally the volume, flipping up down, which is vertically, and flip and rotate, which is a combination of flip horizontal and 90 degrees rotation. Okay, so it's gonna go through each of the patch. We read this data is coming from the random patch generation, which is gonna read 8 patches at a time, both from the input and the expected response, which is the labels, the categorical labels. Okay, so notice that the patch in the input image has the 4 dimensions, the 4 dimensions because it has the 4 modalities of the MRI. That's the color image, and the one is the category of the card, which is 0 or 1, which is 3 dimensions. Okay. Okay, so we're gonna pick a random number between 1 and 8. So we have 5, and if that value is below 4, then we're gonna apply one of the transformations, the affine transformations. And notice that the same function is applied for both the input image and the label image. Because, for example, let's say that you rotate by 90 degrees the input image, but the label stays the same. Then, okay, now the labels do not match anymore with the image. So any transformation, any affine transformation that you apply to the input image, it has to be done also for the labels so that they keep matching. But also, we are interested in doing this for the training data, not for the validation data. That's why we want this checking here. So because this is one, then we're never going to apply this affine transformation for the validation data. So we're going to skip it and just put the image as they are. But then the expected response, as you saw, the neural network output or the patch, the neural network is going to spit a patch of 44 to the cube. So that's why we have to clamp down in order to be able to compare it against the output. Okay, so just let's capture the value for that patch. Okay, let's keep running. Let's put a breakpoint here. Okay, this is gonna be called twice. Okay, again the same error is gonna be committed, so we have to run this again. Okay, the next time this function is gonna be run is gonna be for the training data, so I'm not interested in stopping here anymore. So I'm gonna close this. Okay, now we have the data stores for training, we have the neural network, and we have the training options. But this part in here is gonna download the test data that we're gonna use to validate the trained neural network, and also it's gonna download a pre-trained neural network as well. I'm gonna tell you in a moment why is that. Okay, again, it's gonna put me into a C folder. I don't want that. Oops. So let's put it into the D drive. It's not gonna create anything. It's gonna download the test data. It's gonna use the web save command to download the mat file for the pre-trained neural network, and also for the test data, which comes for the test data. Okay. No, I'm only downloading the pre-trained neural network, and it's gonna. But there's another zip file. Yeah, the sample data is gonna be downloaded from here, but it's gonna use the untar to unzip it. This is important. So if you get a tar file, which is like a zip file for training data or test data, you can use this to unzip it. I didn't know that MATLAB had this command, so I downloaded WinZip. You don't have to because you have this. Okay, let's get out of this. Okay, so we downloaded the data, and now we're going to train the neural network. Okay, so if you have an NVIDIA Titan XP or GPU or something better, this is going to take 30 hours to train. That's a long time to have your computer turn on. So because of that, we get a pre-trained neural network. Notice that to train the neural network, you have to use the train network command, in which you pass the data store, and this data store for training is the one that we created with this transform that takes as an input the random patch extraction data store that takes the image and the label. So you're going to provide in the same data store, you're going to provide the brain 3D image and the 3D labels for training the image. Then this L graph, this is the neural network that we created using these unit 3D layers, and that we modified the first layer and the last layer. That's the one that we provide here. And the options is the optimization algorithm with the validation data and the hyperparameters. So once you run this, you're gonna get a net, which is the trained neural network, and this is the same variable that we're gonna load from this math file. So we're skipping the process because running this command takes 30 minutes. No, sorry, 30 hours. If 30 minutes, that's not a big deal. Okay, so let's take a look at the workspace. So once we run this, we should have the net variable somewhere here. Yeah, there it is, which is the same that this command returns. Okay, so if you want to do the example and train the neural network, you have to change this to true to go through this path and run this for 30 hours. Okay, so now that we have the trained neural network, we're gonna assess how accurate the neural network is. Okay, so for that, we're gonna use the test data, which are the images and the labels for the testing, which should be orthogonal and data that the neural network has never seen before, to see if it generalizes well. We provide again the class name, background on tumor, which correspond to 0 and 1. So this location of images and labels are these ones over here. And notice that we have 5 volumes for 3D volumes of brains and the corresponding 3D volumes of labels. This is the 5 samples that we're going to use for testing the neural network to see its accuracy. Okay, now that we have the location of the test images and labels, we're going to create a couple of data stores, image data store and pixel data store, which takes the location, takes the same volume reader that we have been using all throughout this example. The extension is going to be a math file, and for the pixel data store, we have to provide the class names, this one, and the pixel labels. Okay. Okay, now again, one of the I don't know if you can call it challenge or tedious work for deep learning is that you have to do some pre-processing, like we did before. Notice that the neural network was trained for patches. It was not trained for the full volume. So if you provide as an input the 3D brain image, we have to go through all the patches and then get the corresponding patch for that little patch, and then assemble a 3D output volume of the whole brain. So the volume is a 3-dimensional volume, so that has X, Y, Z coordinates. So in order to get to a 3D volume, you have to go through 3 for loops, nested for loops, to go through the whole volume. So what this is going to do, let's start processing the first volume. Again, it's using the same has data. This is a method again. Let's just show it in here. While it has data, it can be read. It's the same thing as calling a method in the data store. So yeah, I could do the same thing with this method, but the problem is that once you read the data, it's not going to read it again. So I cannot run this because like I run the other one because this is going to mess up the data store. Okay, so we're processing the first volume. We're gonna get output in here. There, as you saw before, the test data has 5 samples, so we're gonna run this 5 times. Okay, so we're reading the labels. This is the labels, the ground truth. So this is the expected value. This is what we're gonna compare against. So notice this is a full volume. It has the 240 by 240 by 152. This is a full volume, so we're gonna put it as it is into the list of ground truth labels. We're gonna use this later for the comparison. Okay. Now we're gonna read the brain image volume. Okay. This is gonna be 240 is the same size as you can see. They are the same size, but these are for it has an extra dimension with the modalities of the MRI. Okay, so now since we're gonna divide this volume by patches, there's gonna be one patch that doesn't fit in the image. It's like for example, let's say that you divide let's say that your patch size is 2 and your volume size is 7. Then you cannot divide 7 by 2. You're gonna have a remainder of 1. So in order to be able to divide it by 2, you have to pad the volume from 7 to 8. Now if you add an additional padding element to make it 8, then you can divide it 2, 2, 2, 2 and in 4 divisions. That's basically what is happening here. You get the input patch size and the output patch size, and you do some computations to know what you have to pad. So you compute the pre-padding and the post-padding, and you use those to with the pad array. You specify the pre-padding and the volume, and then you get a volume that is padded with the input the size and the pre-padding, and then you pass this to another pad array stage, and you post-pad it. And after padding the volume, we get the padded dimensions, which are larger. And then we get the original dimension. The original dimension was 240, 240, 152, and now the padded dimensions are, yes, are a little bit larger. Okay, again, this is gonna be the output segmented image coming out of the neural network, which is called in here. And we pre-allocate the memory. We know the size that it's gonna be, so we pre-allocated it for efficiency of memory, because if you don't pre-allocate it, you're gonna extend the memory for each iteration, and that's is gonna bring your computer on its needs most likely. Okay, so notice that we're doing a range iteration in here. In MATLAB, if you do something like this, let's say we want to go from 1 to 3 with a step of 0.5. Notice that the minimum is 1, the maximum is 3, and the step is 0.5. So go 1, 1.5, 2, 2.5, 3. So that's what we're doing here. But notice that we're picking for the step, we're picking this, which is the output patch size. And the output patch size is 44 by 45 by 44. So the step is going to be 44 for each one of these. And then the initial value is 1. It's going to go from 1 until the depth, the width, and the height of the path minus the input patch size. So this is going to define how we're going to iterate through the patches in the 3D volume. So using the coordinates, the induction variables I, j, and k, we're going to know which segment of the patch we're going to select. So this is the input volume, and we're gonna, the stride is gonna be the input patch size, and the coordinates is gonna dictate where we're gonna take that patch from. So now we run this, and we got a patch which should be 132 to the cube by 4, 132, 132, 132 by 4. So let's take a look at the patch, and that's it, which is the input size of the neural network. So now we're going to use the semantic seg image processing computer vision toolbox function, which takes as an input the trained neural network and the image. The image could be a 2D image or it could be 3D image as it is in this case. Okay, so once we feed it to a neural network, it takes some time to run because this is a big network. So it's gonna feed the 3D volume and get the output patch. As you may remember, the output patch is gonna be a size of 44 to the cube. And you can see it in here, it's a categorical array. That is saying that whether it's a tumor or not. And then we're gonna use the induction variables and the output patch size to assemble to put the output patch into that corresponding segment sub array of the 3D volume. So we're frozen. No, my computer froze for a little bit, but that's okay. So let's put a breakpoint here to see what's gonna happen at the end. I'm gonna pause it because this takes maybe around 1 minute, but I'm gonna show you how computational intensive this is. So right now MATLAB is taking almost 3 gigabytes of memory to run this. It's gonna be using 8% of the GPU, which is, yeah, but it's not taking advantage. I'm recording this video with OBS Studio, and OBS Studio seems to be exploiting the GPU better. Yeah, so I guess these computations can be, I mean, even improved if the example would have used the GPU better. Okay, so I'm gonna pause now. Okay, it finished running, and now we have the collected image, but we don't want the padded image, so we're gonna crop out the extra elements from the padding. Now the output size of the categorical labels, segmented labels, indicating whether you have the brain has a tumor or not, is the same size of the input image, which is 240 by 152. Okay, so we're gonna put the output result into these predicted labels for the sample number 1, and we're gonna repeat this 5 times. So you see that we already processed 1, and then we're gonna go to the next one. The ID is gonna be the next one. Now we're processing volume number 2. So I'm gonna pause again and go hit F5 to get to this point, and it's gonna probably take 5 minutes. Okay, I'm gonna pause, hit F5, let it run, and wait for 5 minutes. It took about 5 minutes to get the data out of the neural network, and we assemble it into this object which we place into here. So now we're going to compare the results of the neural network against the ground truth, the expected labels that is coming from the test data. Okay, so first we're going to evaluate by looking, inspect visually manually a transverse a slice of the 3D volume. Then we're going to compare the volumes themselves, and finally we're going to use a function to compare the ground truth against the neural network for each of the 5 test samples. Okay, so first we're gonna pick up the volume just to look at it. We're gonna in order to see the volume, we're gonna take the first channel, the first modality, and we're gonna use the first sample with this index. So with the first sample, we're gonna take the volume, which is gonna use here. We're gonna overlay the labels or the expected labels against the predicted labels from the neural network. We're gonna overlay into an image, both of them, into a two-dimensional image. So we're going to take the first sample, and the dimensions of this volume is going to be what you know already, the same dimensions that we always have for the brain 3D data. So we're going to use the last dimension for partitioning, taking the slice. We're going to take the middle one, 152, which is third dimension. 152 by 2 is 76. So we're going to pick this element 676 to pick up the slice, and we're gonna do the same for the labels. So we're gonna go get the corresponding label, and now since we're picking a slice, is an image instead of a volume. and the volume image and the label image are going to be overlaid by this function, and we're going to get the slice, which is an image. So we're going to use the montage image processing toolbox function to see both of them and compare them. Okay. Okay, so you can see that they're almost the same. So the good thing is that this test data, again, the test data is independent from the training data. So the neural network has never seen before this image, and it was able to predict which elements of the image have tumor and which one do not. It did it correctly for this slice. Now let's take a look at the volumes. Again, we're working on the first test sample. So we're gonna use the label show that is gonna overlay the volume, the 3 volume that we selected up here. It's going to overlay it with the corresponding ground truth labels, which is expected labels, and then we're going to do the same with the predicted labels, which comes from the neural network, and we're going to overlay both of them the same way. We're going to use again a 0.68 transparency. We're going to use this color map, which is black for the background and red for the tumor, and we're going to hide the background label because otherwise the image cannot be seen, and we're going to do the same for the predicted label. So we're going to see both volumes now. Okay, we run this to take out the background label, and now we have this image. Now let's do it for the neural network output. And we can see that the volumes are almost the same. Almost the same. So let's take a look at how it looks. Poor person. This is a huge tumor, and it did it correctly. You can see that's almost the same. Now let's instead of doing visual inspection, we're going to use the dice function that is going to compare for each of the samples. It's going to compare the predicted labels against the ground truth labels. So this is going to compare how close each of the two categories are from each other. Okay, so yeah, we pre-allocate the memory to avoid pre-allocating the memory for each iteration. So let's see what is the length of the volume. So yeah, so we have five test samples as you saw before in the folder. So we're gonna go through each 5 of them, and then we're gonna compare the corresponding labels between the two, and then store the results into here. Okay, so let's just run it. Okay, so now we can see the output is 5 by 2, 5 because we have 5 test sample, and 2 because we have 2 categories. The column in the left is correspond to the background, and the one in the right correspond to the tumor, non-tumor and tumor. And as you know, as you can see, the image have more non-tumor pixels than tumor pixels. So as expected, the precision is 99% for the non-tumor pixels, and around maybe 95-96% for the tumor pixels, but still it's pretty good. Okay, so let's display the average. Let's take the average of both. So the average of these numbers, of these dice results for the 5 test sample is 99% for the non-tumor, and for the tumor is 96% rounded. Okay, so we can create also a box plot we can just run these commands and we get the box plot. So you can see here that the background non-tumor, but still is pretty precise. Okay, thank you very much for watching.